All right, so looking at these last couple examples here, we have to decide whether or not we're going to use combinations, permutations, or don't forget we have that general counting principle where we multiply the number of ways to do each step. So looking at number 4, we want to know how many committees of 5 people can be chosen in which one is a chairperson, and we want to form it from 12 people. Well, here's what we have to do. We have 2 basic steps in this problem. The first step, we're going to pick the chairperson, and that can be done in 12 ways. Now, what we want to do is pick 4 from the remaining 11, and we don't care about the order that they're being selected in because they're just going to be part of the group. So that's 12 times 11C4, and let's see what that comes out to be. Sounds like an explosive group. C4, haha, get it? And I didn't expect you to laugh anyway. 12 times math, PRB, NCR, 11C4, and that is equal to 3,960. So a lot of groups. A lot of different groups possible. And again, that's because just because a person's on a group or in a group, they could either be the chairperson or not. So that gives us a lot more options. So now let's look at picking letters. So we're picking from the letters A through H, and we want to know how many permutations of the letters, so right there that tells us we're going to be using the P notation quite a bit, contain the following. So we want to make sure that our permutation contains A, B, C, D. So that means that we want to put in order A, B, C, D, E, F, G, and H. So what that means, we want to put 5 things in order. So A, B, C, D happens 5 factorial ways, or 120. Okay? Similar idea with B, C, D, E, F. Now I'm just going to use that as actually part of it. We also want to place an A somewhere, a G somewhere, and an H somewhere. So that's 4 things we want to put in order. So that's 4 factorial, which is 24. I urge you to try AH. Just try it on your own. Pause the video. When you come back, I'll solve it for you. So AH, we want that where B, C, D, E, F, and G could be anywhere. So we have 7 things we're trying to put in order. So that's 7 factorial, which is 5,040. I'll just box my work here so it's more clear to see. All right. ABC and FGH. So we have ABC, FGH, and D and E can pretty much be on their own. So there we have 4 things we're putting in order. So that's 4 factorial, which is 24. Now, AE or AG, here's the interesting thing. So remember we learned previously about inclusion, exclusion. And we know that if we have an or, we're adding outcomes because we're saying we want this or we want this, not and. And means multiply. So looking at this, AE and AG can't happen at the same time. There's no strings of letters that are going to have those 2 things together. So basically, all we do is look at the AE, look at the AG, and then add them. And that's our answer. Now, AE, if you think about this, we want AE together, and that means the other 6 letters can be anywhere they want to be. So that's 7 factorial ways to do that. AG, by the same token, is that. So this is 5,040 and 5,040, which turns into 10,080 different letter combinations, or I should say permutations, that contain either AE or AG. Okay? Last but not least, I'm just going to get rid of my calculator there. Last but not least, so let's say we have an investor who intends to buy shares of stock in 3 companies chosen from a list of 12 companies recommended by her broker. How many different investment options are there given? So part A, equal amounts to be invested in each company. So if we're investing equal amounts in each company, we really don't see them as different. So if I invest $5,000 in these 3 companies versus these 3 companies versus those 3 companies, it basically boils down to, I just want to know how many different groups of 3 there are from the companies. So this is going to be a combination problem. So we know that's 12 factorial over 3 factorial times 9 factorial. And I'm actually going to expand this. I don't want to have to get the calculator out if I don't have to. So expand the top until we get down to 9 factorial. They cross out. 3 factorial is 6, so that's 2. And this looks like 2 different possible combinations of 3 businesses or 3 companies. That's a lot. Now, what if we're investing different amounts in each company? So now this says company A could get 5, company B could get 3, company C could get 1, or company A could get 1, company B could get 5, company C could get 3. So what that means is I can now view those as order matters. So basically, I want to choose which company gets the 5,000. I can choose the company that got the 11,000 or the 1,000 and so on. So this turns out to be a permutation problem. Or if you think about it this way, pick which amount you want to go first. You have 12 choices for the 5,000 investment, 11 choices for the 3,000, and 10 choices for the 1,000. Multiply those together and we get 1,320. And that's exactly what you would get if you did the permutation formula as well. So hopefully this whole interplay between combinations and permutations is starting to make sense. If order has any bearing on your problem, then you're going to want to use permutations. If it's just a flat out group of whatever, it's going to be combinations. So that's all I have for counting principles right now. Thanks for watching. And next we're going to go to the binomial theorem. Exciting stuff.